my goal is sometime tonight, if not tonight, definitely sometime later tomorrow afternoon, to have your tests all graded and the reports sent out. So if you could patiently wait, that would be great. I've got no real excuse except after I teach, I'm kind of exhausted. And so it's hard for me to motivate to do the grading, but I will get it done because it's important to you that you get your grades. You're pretty much finished everything. We've got a couple of more sections to do. Chapter 13 has 2 sections. Yes, Isabel, what's your question?
I was just wondering when you're going to post the final percent grade in Canvas.
Once I've done the test, you will get a report. It'll be called Week 9 report, and that's essentially 90% of what you need to know. The only thing that will be missing from it is the last set of homework.
Yeah,
everything
but
else.
When can we see our overall class grade for the whole quarter?
Yeah, that's what report and Week 9 will have.
Okay.
Each time you do it, I show everything you've done up to that point. So
will
when you get the
presented on Canvas though at all?
No, that'll be sent to you through an email, Isabel. And in that email, I'll have all the information. So
okay.
if you've never seen one of them, then you need to contact me because I'm using an email.
I've seen them.
Okay,
I'm just
that's
curious
good. Right. So it's as I said, it won't be probably won't be today, but certainly will happen sometime by tomorrow afternoon, stroke evening, and that I'll be able to finish off doing everything and send the information to you. And then we'll be ready. So where was I? Yeah. So we've only one last chapter to do, and we're going to concentrate on means. Today we're going to look at hypothesis test for a single mean. And on Friday, we're going to look at hypothesis test for the difference between 2 means. And that's pretty much it. Parker, I hope you are not driving. And if you are, you shouldn't be. Are you okay? I don't think she can hear me or speak to me. It looks like you're in a car, so I hope someone else is driving. Nobody should get killed because of this class. Right, so chapter 13, hypothesis test for a single mean. That's what we're going to do. I'm going to start by giving you the big picture. It's very similar to what you've already done with proportions. There are a couple of little things that notations just a little different. The formulas might be a little bit different, but for the gist of it, it's pretty much the same. So let's do one by hand, actually probably do 2 by hand, and then we'll show you some of the homework questions. Imagine that I have a population, and in this population, we're only looking at self-identified males. And I am interested in seeing if there's evidence that adult males average IQs are more than 97. So I believe that an adult male has an IQ, the average adult male at least, has an IQ that's more than 97. And so we are going to try and set up a hypothesis test to see if we can prove that's true or not. Now, whenever you have a statement like this that you're trying to prove, you should have a guy called the significance level, and we're going to use 0.05 in my story. So what you then do is you set up a null alternate hypothesis, and then you collect a sample, and you see if the sample can prove what you hope is true. Well, the null hypothesis and the alternate, right? So the null hypothesis is that it's 97. And we're trying to prove that it's greater than 97. Can you see how we can realize in this story why it's a more than, right, a greater than. Let's talk about names of these. What name do we give to a hypothesis test that looks like this, that has a greater than going on? It's the same name that you used in proportion. Right-tailed or...
tail?
Okay, I was going to give you a choice, but you got it right away. It's right-tailed test. If I wanted to prove that their IQ was actually less than 97, wouldn't that be called a left-tailed test? And if I wanted to prove that it was different from 97, wouldn't we call that a two-tailed test? So you've seen some questions where they say, what kind of test is it? That's where that's coming from. So essentially, step one is set up the null and alternate hypothesis. That's cool. Now, step two is that we are going to calculate the standard error of our sample. To be able to do that, I have to collect a sample. So let's suppose that I collected some data on 200 adult males and that the mean I got was 97.8 and that the standard deviation of my sample was 0.9, okay? Now, based on this sample, right, 200 people, their average IQ was 97 and a bit, and the standard deviation of that sample was 0.9. Once you've got that, you pretty much have everything you need. There is a formula for the standard error. We used this formula when we did confidence intervals. Can anybody remember what the formula for the standard error is? And it uses these numbers, or some of these numbers here.
Mm-hmm. Is it S over the square root of N? Or is it
Is it? No, you're right. That's exactly what it is.
Yay, I wasn't sure. That was a shot in the dark.
Right. So there you go. 0.9 over the square root of 200. So I'm going to put that in 0.9 divided by the square root of 200. And that is 0.064 to 3 decimal places. So step two is find the standard error using this formula. Now you can't do that until you've got this information to play with. That's fine. Step three is we're going to get what the book tends to call the test statistic. In this case, it's going to be called the t-score. And the bottom is the standard error, which we've just calculated. So that's going to be 0.064. And the top is going to be X bar, take away a guy called mu naught. And you're thinking, where did that guy come from? Well, let's do X bar, 97.8. Do you see this number here? Mu equals, in this case, mu equals 97. That's the guy that we call mu naught. So if you do a hypothesis test and mu is 50, that guy there will be 50. If you do a hypothesis test and mu is 1,000,000, that guy's going to be 1,000,000, right? So do you see where you get your mu naught from? You get it from this guy here in your null hypothesis. So in this case, it's going to be take away 97. And here we go. 97.8, take away 97, divided by 0.064. And the answer I get is 12.5. I want you to think of the t-score as being equivalent to a z-score. Would you agree that a z-score of 12.5 is huge? It's very, very rare. Isabel, your question.
Oh, sorry. I guess I didn't lower my hand from earlier.
Okay,
My
no
bad.
problem. So I can tell, even although I haven't calculated the p-value yet, that this is going to be extremely small, right? big t-scores make small p-values happen, right? A big t-score means it's very unusual. The p-value is how unusual, right? Well, very unusual is like 0.0002, that kind of unusual. So the next step is step 4, where we're going to find a p-value. And the p-value is the probability that you get a t-score. It's either bigger than 12.5 or less than 12.5. Now, do you see over here the greater than symbol? Right? That tells me I'm looking for 12.5.
Does that say t-score?
Yes.
Okay.
So the t-score greater than 12.5. That's the end of me being able to do it by hand. What we're going to have to do now is use SOLE, right, to find this p-value. So let me switch over to SOLE and show you where you would put the numbers in to get the p-value. Right? I'm going to make this guy nice and big. Hit the distribution calculator. Make sure it's in over here is t-distribution. And it talks about the degrees of freedom. In my story, there was, I've forgotten how many people there were. There were 200 people. What number is the degrees of freedom if there's 200 people in your sample? It's not 200, but what number is it?
199.
Yeah, you just knock one off it. Now, in the story don't we want a greater than? If you're going to do a greater than, which one of these dots does a greater than?
Right tail.
Agreed? Right tail. And so I go over here and I say greater than 12.5. And the answer is, for all intents and purposes, isn't it so small that it's basically 0? And that's how I got my p-value.
Where'd you get the 199 again? Sorry.
The sample size is 200. So you take sample size minus 1. So degrees of freedom are n minus 1. Sample size, take away 1. So 200 take away 1, 199.
Okay.
Right, now I'm returning back to the paper to finish this story off because that's the only bit there I need to leave and do salt on. The final stage is our p-value unusually small? Is it less than alpha? Is 0 less than 0.05? And the answer is yes. So when that happens, can't we do a conclusion? And our conclusion, and there's different ways they phrase it, but one of the ways you can say it is there's enough evidence to reject H0. So there's enough evidence to say that's not true. That is the equivalent to say there is enough evidence to prove the alternate is true. So if you say this in statistics, it's equivalent to saying that. So if you can reject the null hypothesis, in that same breath, you're also saying there's enough evidence that the alternate is true. So in this case, isn't there enough evidence to prove that male IQs are greater on average than 97? In fact, based on that p-value, couldn't you pretty much bet your house on it and you'd be true, right? It'd be very unlikely you got it wrong. Okay, let's do another one by hand, except for the p-value part, of course. And this time, we're going to have, we're going to have college students. And we believe there's evidence that a typical college student sleeps less than 7 hours on average per night.
Is this a continuation of step 5 or is this a separate problem?
Separate problem.
Okay.
So this is, we believe that a typical college student sleeps less than 7 hours, and we're going to try and see if we can, prove it. So there's going to be a significance level of 5% again. And my null hypothesis and my alternate is the kind of the starting point for the story. Mu is the average number and it's equal to 7, right? And mu less than 7 is the alternate. Are you happy why I chose less than 7 in this story? You comfortable? Less than 7 hours sleep, mu less than 7. So far, so good. Now, I collected some data and I got 50 students, just call it N, and the average number of hours that they slept was 6.9, and that the standard deviation was 0.2. So this is the information that I got from my experiment, right? My sample. Let's look at calculating the standard error then, because that's step 1 done. The standard error in this sample is S over square root of N, 0.2 over the square root of 50. And 0.2 divided by the square root of 50 gives us 0.028. Move on to our test statistic. And our test statistic is X bar, take away mu naught, divided by the standard error. There's the standard error. Okay, X bar was 6.9. What number is mu naught in this formula?
7.
7.
Great. That guy there. That's what mu naught is. Well, on my calculator, let's find out what the test statistic is. It's going to be negative, that I can say for sure. And I got negative 3.57, roughly. And this fella is called your t-score, right? Your test statistic is called your t-score. Right, now in stage 4, we are now going to find our p-value. And that's the probability that we get a t-score. Is it going to be bigger than or less than this number?
Less than.
And how, correct, how do you know?
The alternate.
Yeah, if it says less than, make that less than. Right, isn't this the place where we would then go and use salt, right? Because we can't do this by hand, right? We have to do it using salt. So I'm going to go into salt again and hopefully set this fella up. Right, now, in this case, there was only 50 people in the sample, so won't the degrees of freedom be 1 less? That's where the 49 came from. We are looking at a less than, aren't we? Which is a left tail. And we are looking at less than -3 So I'll put the number in, negative 3.57. And the p-value we got is very small, but at least it isn't 0. 0.00041. Okay, I'll return now to the whiteboard where you'll see that information. So we now have our p-value. So we should be able to do our test or check. Is our p-value small enough? Is 0.00041 less than 0.05? And the answer is yes, isn't it? And because it is yes, won't we come up with the same kind of conclusion that we did the last time? There is evidence to reject H0, which is the same thing as there's enough evidence to prove that the alternate is true. Haven't we shown then that college students sleep on average less than 7 hours per day? Right, our p-value is so small that this guy here is a yes. Eric, question.
I think I just figured it out. Never mind.
Have you noticed how good I'm getting, guys? I'm now using telepathy. People think of a question, then I just send the answer to you telepathically. Do you believe that, Abra?
Sure.
Ah, okay then. Right, watch this, Abra. I have just telepathically sent you a digit from 1 to 9. What one did I send you?
5.
Nah, darn it, I sent you 7. You're just not
I
focusing.
knew you were going to say 7, so
Oh,
I
you
said a different
deliberately
number.
not. Now, the fact you knew I was going to say 7, doesn't that mean that telepathically I was sending the signal?
I mean, I guess.
Right.
No, because statistically somebody's going to say 7.
More often than the others.
Yeah, we actually proved that.
We did. So in a way, I guess that's a little bit of a cheat. Are we comfortable so far with this process of how you would set up a hypothesis test based on a single mean being bigger or less than some given value that we're interested in? We're good with that? Right, so they're going to be, in a few minutes anyway, we're going to look at some of the homework questions because they tend to, do things their own way. The first lot are really going to be just general questions, and then the second half of it is going to be using SALT, because what we really want to do is do this entire process using SALT rather than us doing any of it by hand, right? Wouldn't that be the best way to tackle this? Right? So let's look at the homework questions, and then eventually we'll get to those ones where we can use SALT. And there we go. And can I make this bigger? Because if I can, it would be, okay, that's good. Now, these are, I want you to think that a lawyer got involved here. So you have to be very precise about what is going on here. So it says, explain whether each of the following statements is true. So one of the two possible conclusions that you can get in a hypothesis test is to accept the null hypothesis. Have I ever said we accept the null hypothesis? No. False. In hypothesis testing, can only be used to show that the alternate is true. Have you noticed that when we do, the way we phrase it is, we've managed to reject H0, so the alternate is true. We never say we've managed to prove H0 is true, right? So that's the lawyerisk one. It was the fourth thought. Now, when you say reject the null, is it the same thing as accepting the alternate? Are they equivalent statements? And I did mention that today. Is rejecting the null hypothesis the same thing as saying the alternate is true?
Yes.
It is. So one of these two is the right way of saying it. So let's see what that one says. Would be correct at any time. A hypothesis tends to prove a certain true. Try that one. Both these statements would be correct conclusions anytime the hypothesis the alternative hypothesis is true. There we go. Now explain whether each of the following is true. A hypothesis and its conclusions from a hypothesis test apply only to the samples. So when we come to a conclusion, do we say that there's evidence to prove the sample is bigger than 7? Or do we say there's evidence to prove that the population mean is bigger? Which of those two do you come?
Population.
It's a population one. So this statement is not true. Hypothesis conclusions are statements about the population. Now, the p-value is calculated with the assumption that the null hypothesis is true. Actually, it is. The p-value is calculated with the assumption that the null hypothesis is true. For these questions, can I make that bigger without losing time? Okay. For each of the following research questions, specify whether the parameter of interest is one population mean, the population mean of a paired difference, or the difference between two of them. Okay, here goes. Residents of a neighborhood have been complaining about speeding cars. The speed limit in their area is 25 miles an hour, and the local police monitor the situation by recording the speed of 100 randomly selected cars. They want to know whether the mean speed of all cars that drive through this area is higher than 21. So that's basically your story, right? Would you agree that we're looking at just one population mean, the speed of cars? So that's that one. And I'll let you figure that one out. Explain why a standardized statistic is used in hypothesis testing. Right, why do we use t-scores? Would be a better way to phrase that. Well, you could say, well, let's do it the other way. If I took the difference between the sample mean and what the population was, and the answer I got was the difference between them was 2. So IQs are 100, but my sample said the average IQ was 102, right? If I just used the difference, it would be 2. That's not enough to tell you how unlikely that is. See, if you only asked 4 people, couldn't you get a difference in 2 dead easily? If you asked 20,000 people, wouldn't you get a difference in averages of 2 would be highly unlikely, right? That'd be a pretty rare event. Don't you need to incorporate not just the difference, but the sample size and how varied it is? That's why we use our t-score. So one of those sentences basically goes into the same thing. Now this one, explain why the null hypothesis for a significance test is rejected when the p-value is small rather than it's large. I've said this lots of times. If the p-value is tiny, does it not mean it's highly unlikely that what you saw in your data happened by chance? That's essentially what the p-value is telling us. So the p-value measures the probability that the null hypothesis is true of observing sample results as extreme or more extreme than those observed. If the probability is small instead of large, it indicates that the sample results would be unlikely if the null hypothesis is true. So that's me just trying to put that into a sentence using those. Okay. Here is some setting up null and alternate hypothesis questions. A botanist for a large rose farm is told that the company currently averages that many $1,000s of sales. The company hires someone to work as an outside consultant in order to increase the revenue. The null hypothesis is that the revenue stays put as 339. What would the alternate be if this person that they hired did their job? What would you expect? Which one of these four would you expect as the alternate?
Mu is greater than 339,000.
Agreed. What kind of test do you call it when it's a greater than? 1 or 2? They don't even give you the choice of right. So there's that one-tailed thing, right? So there's an example of them asking you about tailed. A chemist believes that a cornfield must be treated with a fertilizer on average 4 times over the year to get optimum growth. However, she's curious that maybe she could do it with fewer treatments, right? Save money. The null hypothesis is that you need 4 treatments. Okay. What would the alternate be? She thinks she can get away with fewer. So what would the alternate be?
Less than.
And there she go. Is that a 1 or a 2-tailed test? Right. Are we getting a little bit more comfortable with the alternate null hypothesis setups? Right. Here's another one. A botanist believes that a pumpkin patch must be treated with a fungicide 5 times to get optimal plant health. However, he's curious whether he could do equally well with fewer. So won't it be, oops, isn't that always equals? And he thinks, or she thinks, I'm not sure if it's a he or she this time, listen. Oh, you can read that one. Do you know the steps that I did on the 2 examples? That's essentially the same steps. So in this case, we're going to have a story, and it asks us to define the parameter of interest. So in the story, there's going to be the average weight, the average IQ, the average tire pressure, something like that. So define a parameter of interest and then use it to write the null and alternate. So here's our first story. Many cars have a recommended 33. And we are interested whether drivers have too little pressure. So if I click on this guy, it should say mu equals 33, right? That's what we would have expected if nothing's going on. So hit the Greek letter and pick the guy that looks like mu. I know he's in here somewhere, there we are. And mu equals 33. What is the alternate going to be in this story about tire pressures? We think people don't blow up their tires enough.
Less than.
Right, so in this case, you're going to go and hit the Greek letter. You're going to type in mu, and you're going to go less than 33. Do you notice it's always the same numbers? Isn't the null always mu equal that number? And isn't the alternative bigger than 33, less than 33, or not equal to? If you have to do a not equal to, don't you have to do that really weird exclamation mark equal thing? Right, that's the guy that we do. All right. Yvette's favorite cereal.
What about
State-
what about
Right.
the first word part?
Oh, I missed that. You're right.
Parameter of
So
interest?
the parameter of interest here, what are we measuring in this story?
Tire pressure.
Tire pressure. So one of these sentences is going to be the tire pressure of a typical car, right? The population average for tire pressure. So the parameter is the difference between, no, the parameter is the average tire pressure of all cars. There we go. It's that one. Okay, let me make sure I do this one. Yvette's favorite cereal has a content of 13 ounces. Yvette is suspicious that she's been shortchanged, right? Because when she opens up her box, you ever done that? You open a big box and there's like 4 inches of air before you even see the stuff, right? She thinks she's getting shortchanged in her story. So being a scientist, the next 30 boxes that she buys, she weighs them. I guess she pours out the contents on a scale, right? She weighs them. So isn't the parameter of interest here the average weight of cereals, right? So let's see which one of them. It's the average weight of the content for the population of all Rebel network contains that, right? So there we go. Now, in this case, the null hypothesis is that there's nothing to see here and she's getting what she should get. It should be 13. She thinks she's been shortchanged. So what will the alternate look like?
Less than.
So less than. Can you see that they're just getting you practice at setting up the null alternate hypothesis here, right? You're not doing any number crunching yet. Now, the next question, question 11, I think I can make that bigger because it's such a small thing. There we go. They're asking us to do the t-score. I call it t-score. They're just calling it T for short, right? Can you remember the formula for t-score? We did it at the start of today. Right. Can you remember the formula for the t-score?
It was
X.
the x minus the mo over se of x. right?
Yeah. So can you see that in this question, since there's no salt involved, doesn't that mean we're going to have to do some calculations, right? So I'm going to have to leave this for a second and I'll just pick one of them to show you how you would go through that entire calculation, just to get what they call the T. I would call it the t-score. So in question A, that's the one I'm going to do. You know that the null hypothesis is that the mean is 45. Okay, that's fine. You're told that X bar is 65. You're told that S is 70. And you're told that N is 121. Okay, so that's pretty much everything we need. I need to calculate the standard error. So that's the first thing I'm going to do. It's going to be that guy. So it's going to be 70 over the square root of 121. So I'm going to go to my calculator and I'm going to go 70 divided by the square root of 121. And I'm looking at 6.364 to 3 decimal places. And then what I would call the t-score, what they call T. It's just like you said, it's X bar take away mu naught over the standard error. X bar is 65. This number here is who mu naught is. So it's take away 45, and you're going to divide it by 6.364. So put a bracket around it, 65, take away 45, divide everything by 6.364 and 3.143 to 3 decimal places. Are you comfortable about how to get the t-score? It has a number of names. It's T, it's called t-score. You will also find it's called the test statistic. Right. And who knows, maybe another name, I don't know that. I'd be comfortable with how we calculated the t-score. Provided you give me this information here and I know that number, we got everything that we need. So here is another question. This is question 12. In question 12, we're told that the null hypothesis is that mu equals 260. We're told that the sample mean was 272. And we're told that we actually were told that that guy is 4, at least I believe we're told that is 4, and we're given the sample, it's 100. Now, if they have told me that, then I don't really need to know what that is. So here goes, our t-score is x bar take away mu naught over the standard error. And so that is going to be 272 take away that guy there is mu naught. And I believe it's divided by 4. And the answer I got would be 3. If they didn't tell me the standard error, but they just said instead that the standard deviation was 4, then wouldn't I have to calculate my standard error by taking 4 and dividing it by the square of 100, right? So that was sneaky. I almost get caught out. Well, what we're now going to do is use salt to do essentially the whole thing, right? So we won't need to do any of this stuff here by hand. We're going to let salt do everything for us. So it's going to take me a few seconds to hopefully get this set up, and then we're ready to go. Okay. Are you looking at a double page thing here? Okay, so find the p-value. Don't worry about drawing the sketch, we'll see that in the picture. For the following story. And essentially all the information that we need is here. We're just going to find the p-value, right? So go to your calculator. Make sure you're in distribution. T distribution, degrees of freedom, right? Can you see how there's 29 here? What number is the degrees of freedom going to be? Well, 28, I saw fingers, so I'll call it 28. Now, in this story, would you agree that we're looking for a greater than? So I'm going to go over here. And maybe I could shrink it down a little bit, that might help. If you're looking for a greater than, isn't it right-tailed? And then you can go over here and you can put in a t-score of 2.4. And this guy here is the p-value. And to 4 decimal places, he's that guy. Now it says draw a sketch of it. If you go over here, can you see the sketch as a big hill with a little bit to the right shaded? If you look at our guy, would you agree this is the picture that's closest to that one? So that's how I figured out what that picture was. Now, similar. Are we good? Right. Right. Now, in this one here, it's a greater than again, 29 and negative 2.4. So, since it's a greater than, right-tailed, 29, same degrees of freedom. The only difference is that I'm going to put a negative here. Do you see that the p-value is ridiculously big? And it looks like that guy. And when you look at the picture, Can you see it's mostly shaded to the right? And that makes it this one. So if you want to find just a p-value, you can do it through SALT. But if you're going to do it through SALT, you need to know sample size and you need to know the t-score. Suppose a study is done to test the null hypothesis that the mean is 100. I think I'll have to do it this way and shrink it. That's probably the best way. Right, here we go. Where the heck are we? I think we just finished that one. We did, right. Suppose a study is done to test the null hypothesis that the mean is 100 for the population. A random sample of 47 people. This is the mean. This is the standard deviation. So they're telling us all that. It says, what is the null standard error? That is just another name for the standard error of X bar. So that is going to be S divided by the square root of T. I would just call that guy the standard error, but they want to call it the null standard error because they felt like it, I guess. So that's going to be 14 divided by the square root of 47.
Shouldn't I say the square root of n, not t?
Yes. Now, if I was going to do it without SALT, wouldn't it just be 14, that guy, divided by the square root of that guy? Agreed? Let's find it using SALT. So I'm going to shrink that up and I'm going to go here. And to find out what the standard error is, I'm going to go to inferential statistics. One sample T. Now, in this story, the mean was 103. The standard deviation was 14. And they told me, or they asked me, I should say, to just put in the sample size. That means I don't need to spend any time trying to figure out what the sample size is. So I'm going to have to go over here and find out it's 47. Okay. So these three numbers come from your sample: the mean, the standard deviation, and how many people are in your sample. Now, we are going to test that it's 100. And I'm going to make, let's see, plug a correct number. On the basis given that the p-value, oh darn it, this up and down's not great.
How do you know that it's less than?
I don't know yet. I'm trying to read it and find out. And there should be a clue somewhere in the sentence. On the basis of the p-value, so it can't be found, give that right. If the p-value can be additional, if you, would you agree that we don't know the alternate? We don't know what the alternate hypothesis is. Is it less than? Is it more than? Is it not equal to? Without that, I can't tell if it's a left-tailed, a right-tailed, or a not equal to. Agreed? So I'm picking that one. Now, I can still calculate this fella because these don't care what the alternate hypothesis is because we have all the numbers, right? We have these guys and so on. So I should be able to at least get that done. So I'm just going to call it less than. I don't care. When I hit generate, I should still be able to get my guys. Can you see that fella? On to my question. Yeah. So that fella is him. And should I be able to get the t-score? Sure. Isn't that the t-square? And whatever it is, 3 decimal places, I think. So I should be able to get these two guys. I can't get the p-value because, as far as I can tell, nowhere in the story did they mention what the alternate is. Am I trying to prove it's bigger than 100, less than 100, or not equal to 100? And that's going to change the p-value, isn't it, from one number to the other, depending on what I did. For instance, right now the p-value is 0.92, and that's because I said less than. Suppose I made it greater than. Those numbers didn't change, but do you see the p-value has changed? Suppose I decided that it was not equal to. Can you see that these guys don't change? But you'd have to check that, but that changed as well. So that's why that one I can't do, because I need to know the alternate. Again, try to keep track of time to make sure we get these all done in the time we've got. Right. Here is some information. It's been hypothesized that the mean pulse rate of college students recording their gender and their pulse rate, and let's put it in a full picture so I can read it more. It has been hypothesized that for college students, it's about 71 beats per minute. A sample of university students recorded their gender and their pulse rate, and the data is here. So for instance, in females, there were 34 people. That was their average pulse rate, and this is the standard deviation. And for the males, these were the numbers from the sample. And we are going to be doing 2 different questions. The first one, we're going to check it for males, and that's what all these are about. And in the second one, we're going to check it for females. Let's look at the raw data. Do you think there's more likely to prove that females are above 71 beats? Do you think there's more likely to be evidence that that's true than if it's males? Just looking at that table of values. Yeah, would you agree that women are definitely, at least on this sample, significantly bigger than 71? Would you agree that the males aren't even close to being 71? Right, so I'm going to choose the female one to do the question for. Right, so I'm going to use those numbers and we'll see what we can do. So the sample mean for the women was 76.
Couldn't you just do both of them with a 2 sample T?
You could once you do the next section, but right now we're only allowing us to do singles. So we're doing it as 2 separate questions. So this is the females. Okay. 11 point, it'd be much more efficient, wouldn't it, if you just did both together? But in that case, you'd be testing the difference between the 2, not comparing them against 71. And the sample size was 34. And I want to see, is there evidence to prove that it's greater than 71? So when I hit generate results, can you see the null is it's 71, the alternate is it's bigger. There's your standard error, there's your t statistic, and there's the p-value, which is essentially the guy that's going to decide is there evidence or not. So the p-value goes here, and the test statistic that they're calling it is this guy, goes here. And I'll round this guy off to 2 decimal places, and this other one I'm going to round it off to 4. Now, is this p-value less than 0.05? So one of these works. don't you reject H naught when that happens? And you are going to reject H naught, and you're going to say there is significant evidence to conclude that females have a higher than 71. So it's this reject naught, not that one. Now it says write a sentence that would summarize that. So the data provides sufficient evidence that the mean pulse rate, oops, that's the wrong one. That's for the males. So I'll go here. The data does provide sufficient evidence that the mean pulse rate for females is different from 71. Actually, we proved it's bigger than 71. Is a hypothesis test for this situation in which a decision leading to an action is required? Okay, now that we know that women's heartbeat is bigger than 71, do we need to do any more? Not in this story. Can you imagine that it was a different story and we managed to prove that the new drug was better than the old drug? In that case, wouldn't the situation be, well, start using the new drug, it's better. If we could prove something that is, do the tire one, right? Suppose we proved that people's tire pressures were less than the 33 that they should be. Couldn't the action then be to try and persuade drivers to, you know, increase the pressure in their tires, right? Do advertisements on TV, you know? It's dangerous to drive with your tires not inflated properly, especially when there's ice around or something. Or, I don't know if you're allowed to do it in America. You can do it in Britain. Do you know in Britain you can stop vehicles, and if they fail any safety check, you fine them? So if your tire pressure is lower than it should be, you get fined. If your brakes don't work, you get fined. If your headlights don't work, you get fined. Did they do that in America? Can they just randomly stop vehicles and give them a safety check, as it's called?
They'll stop you if your like tail light or your headlights out,
But
but they don't always give you a ticket.
Right. Do they
But they
stop?
can.
Yeah, they could. Did they stop you like they just go to your street and they stop the first 150 cars and they check every single one?
I don't
So-
think they can randomly pick people.
Right. So in America, it's not allowed, right? If you
They
ever
do
drive,
that for DUIs though.
right, they can just randomly stop on 15 test years old.
They generally set up a checkpoint on like a certain road that they know has
Pubs
a
near
large
it.
amount of drunk drivers, and then cars that drive on that road get stopped and checked.
It sounds to me like we're much more severe in Britain then. So when you're looking at driving in Britain, don't be surprised if you get stopped and you've done nothing wrong. I guess it's a different culture. Because it's a safety check, I guess that's the legal loophole that they use. We're just checking to make sure your car is safe. And the fact that you get fined because it wasn't seems a bit unfair. Okay, let's, what we got? Yeah, we got 10, good. Question 16, an earlier exercise posed the research one. So we're back to the cars and the pressure is 32. So I'm setting up the null hypothesis equals 32. And we believe that the real answer is less. Now I'm going to write down this information because it's going to go away. We got 60 cars in our sample. The average pressure was 29.3 and the standard deviation is 3. I'm getting all of that information basically from here. So when I go and we do this fella, I should be able to set it up. So the sample was 29.3. The standard deviation was 3. The sample size was 60. The null hypothesis was 32, and we're trying to prove that it's less than that. Are you comfortable about the 3 numbers came from the sample and these came from the null alternative? So when I hit this guy, all the numbers that we could possibly want are here. What do they want? Well, they want the test statistic, which is that number. And they want the p-value. Sometimes the p-value is so small. Can you see it here? It's tiny. So when you're putting the value in and you round it off to 4 decimal places, or in this case, when you round it off to 2 decimal places, can you see that sometimes the p-value ends up being 0? It's so small that when you round it off, it's 0.40. Now, based on this p-value, is this less than the significance level of 0.05? Yeah. So when that happens, you reject the null hypothesis because its p-value is smaller than that. Now, what conclusion do you make? We can conclude that on average, drivers have too little tire pressure. So you're right, people don't blow up the tires enough. Are we cool with that question? Right. So for the time I've got left, I've got enough, I think. Let's move on and do a couple more. A cell phone company knows that the average length of call is 9.4 minutes. The company thinks that they might be able to offer a senior discount to new customers, but they only want to do that if senior people use the phone less than 9.4 minutes. Otherwise, you know, they're given them a cheap rate and they use the phone too much. Yes. So what they did is they conducted a little sample, and basically all the information about the sample is in that headline there. So let's set it up. We are going to make the assumption that it's still 9.4. And we're going to try and see if there's evidence that more senior people use it less than that. And the numbers I'm going to use in my sample are 100 people. So that's the sample size is 100. The mean X bar is 8.1 and that the standard deviation is 10. So those 3 numbers, 100, 8.1 and 10 are going to go in here. So the mean 8.1. That guy 10. Sample size 100. We believe that this number is, darn it, I forgot what this number is. It is 9.4.
Your sample mean is wrong.
Oh, there's a 2 there for somewhere. Don't know where that came from. This number here is 9.4. And we're hoping to prove that it's less than. So that's pretty much the sample information, the hypothesis test, and that it's less than. So when I generate results, yep, that matches. Can you see the t statistic and the p-value? So let's take this p-value and just plunk it in here and round it off to 4 decimal places. Is that p-value less than 0.05? No. So when that happens, don't you fail to reject the null hypothesis? So we can't say that older people use the phone less than everyone else. Then they go on in part B and they talk about, that's down here, that number that I just calculated, actually, hey, they've told us what it is, so that's good. They said, pretend for a minute that you got the exact same results, but you got it from a sample of 400. Right, so I'm keeping everything else the same, and I'm just pretending that the sample was 400. Do you think that t statistic and then the p-value are going to change if you got the exact same average and standard deviation, but from 400 people? Great. Let's see how it changes. Oh, quite significantly. Do you see that p-value is a much smaller answer? In fact, isn't that p-value less than 0.05? So in this second situation, we could say that when it was 400 seniors, it was reasonable to reject the null hypothesis. Thus, using a larger sample size did make a difference. So if you conduct a hypothesis test, but you don't get any significant result, right? The p-value is 0.7, right? You can't do anything about it. You could just give up. Or couldn't you go back and maybe ask 5 or 10 times more people and then hopefully get a significant result that way? Any questions? Are we beginning to get a theme now of how these stories work? Right, this one's another one about cars, so I'm going to skip that one. This one, wow, perfect timing, we're going to be finished. A herd of 1,500 cattle was fed a special high protein diet for a month. A random sample of 45 gained 7.3 pounds and that the standard deviation was 5.1. So that part there is all the numbers that you need from your sample. The N is 45, that's how many cattle you checked. The average weight gain was 7.3 and the standard deviation was 5.1. So I'm writing them down because it's going to be helpful. Now, they even tell you the null hypothesis is at 7, because that's what typical cattle gain, right? And do these ones on the special high protein diet, is there evidence to prove it's bigger than 7? Let's find out. Our sample, 7.3. The standard deviation was 5.1. I got that from the story. The size of the sample was 45. And we want to see, is there evidence that the ones on this diet, this protein diet, is bigger than 7? Bad news, isn't that not a very interesting p-value? So you're spending money and you're not getting any benefit, right? You're putting them on a high protein diet and you're still getting about 7 pounds anyway, right? Nothing to see here. And that's kind of what you put in here. Oh, our last question. The average height of children who are 2 years old is 34 inches. Okay. A random sample of 35 children. So here's my sample, 35. In a daycare center, a daycare franchise, they found that the average height of the kids was 28 inches. And the typical height of a kid is 34 inches. They want to, oh, and I need the standard deviation is 1.7. They want to see, is there enough evidence that kids in daycare centers tend to be shorter than the general 2-year-olds are. I hope that's not true, but let's find out. The sample mean was 28 inches tall. The standard deviation was 1.7. And the sample size was 35. A typical kid is 34 inches, and we're trying to prove the daycare kids is there evidence to prove it's less than 34. Are you comfortable about the numbers from the sample and the numbers from the hypothesis? It's got a kind of flow to it. So when I hit generate results, I'm going to have a whole load of numbers. Wow, look at that p-value. So I'll have to go this way, I guess. I'm just going to put in the p-value. You can put in the t-value yourself. To 4 decimal places, isn't that a 0.000 thing, right? Would you agree that is less than 0.05? And when that happens, don't you reject the null hypothesis? Which means that kids in daycare center, according to this at least, are shorter than normal 2-year-olds who don't go to daycare. Now, this is probably just created data. I don't have any reference that said, you know, where it was done and what year it was done. But let's just pretend for a minute that it is done, because very often when you come up with a significant result, you try and see, is there anything you could do about it? If kids in daycare center end up being shorter than kids who don't go to daycare center, is there any reason you can think of? Because I've asked this question to my other class and I couldn't think of one, but they gave me a couple. Is there any explanation for why that could be happening?
Maybe they get more caffeine.
I hope 2-year-olds don't get caffeine, but I guess they could.
They could be eating less.
Right.
They're probably not sleeping as well.
Right. So, I mean, if you take a 2-year-old and I'm not saying rip them away from their parents, but it's pretty stressful. Would you agree? That they probably don't eat as well or sleep as well. And, you know, when you're a kid, what goes in changes you, right? So if you eat a lot, you'll either go fat or you'll go tall, right? Sometimes you'll do a bit of both. But if you don't eat a lot, isn't the chances you're not going to grow as tall, right? So maybe that's it. So you might be thinking, you know, if you're a parent and this was true, make sure your kid gets lots of food, right? Even if that means you feed them when they come back from daycare, right? Because they might not be that interested while they're at daycare. You know, lots of distractions, like lots of 2-year-olds crying, you know, that maybe stress them out and they don't eat. That would be a good reason. I got another reason that someone told me. I actually get 2 more reasons. Anybody want to come up with another one? I like that one. Okay, here's one of them. The kids at daycare center are probably not breastfed as much as the ones that were. And there's pretty good evidence, isn't there, that children who are, you know, use their mother's milk, don't they tend to be healthier in lots of ways? So you're nodding now, bro, like, yeah, that's a good thing, I believe so, right? So if you take your child and you put them in daycare, would you agree they're not getting breast milk anymore, right? In fact, the chances are they probably never got it. Because I'm assuming that if you put your child in daycare when you're 2 years old, you've probably got a job, haven't you? And so you've probably, you know, had to deal with that issue of not having the ability to do that.
I mean, they can pump. Mom
Yeah,
can
I guess
pump.
so. You could. You're right. It's not totally exclusive. Anybody got a third one? Because I've forgotten what it was now. Why would kids at daycare be smaller than general kids? I wish I could remember the third reason. Someone told me and I thought, oh, okay, that could work.
Could it be either stress or they get sick more often?
Oh, I never thought of that. Yeah, if you put lots of, aren't 2-year-olds breeding grounds for germs? Right, if you put a whole bunch of them in the same room, the kid might not go out, he might come in okay, but isn't the chances he's going to come out with something? And if you get sick enough times, it might affect your height. Yeah, why not? We are done for today. We have finished one of our 2 sections. So on Friday, you are going to get hypothesis test for the difference in 2 means. And we are finished. Everything for the test. Okay, I'll hang about for questions. Bye-bye for now. Oh, make
Thank
sure,
you.
yeah, make sure you do your last name and attendance thing.
I hopped in late. Did you say anything about tests?
Yeah, I excuse me. I just haven't got the energy to do them as quickly as I would. I'm going to be doing them later on today, but not right now. Right now, I'm going to go to bed for a couple hours, which is kind of my modus operandi right now. But I'll try and get started later on this evening, and I'll definitely get them done by tomorrow evening. So by Thursday evening, you should get. I know, Abra, because I saw yours just inflating that. I haven't graded it. You haven't been given the extra credit, but you did okay from what I remember saying. Have you
Better than
seen
the
your?
last ones?
Yes, better than the last
Oh,
one.
good. Okay, good.
So if you're, I hope that takes some of the stress off. I can't tell you the details because I can't remember, but I do know that you did pretty good.
That's okay. I realistically, stress is not a thing this week. I'm in Maui. So
Where are you?
I'm in Maui.
You bloody show off. That is not nice. What are you doing in there?
My best friend lives here, and she's been my best friend since like junior high school.
Can
And-
your best friend become my best friend?
I'm here to celebrate our birthdays. So
Yeah, that's what you say.
mhm.
Yeah, Hawaii is one of those places I want to go and visit.
I've never been to Maui, but I've been to Oahu like 7 times. So
So I should have realized that there are palm trees in the background, and that's kind of the clue.
yeah, and I'm wearing a swimsuit because we just came back from the beach.
Oh, that's it. No more.
I don't get the
That's-
extra credit for my
I'm
test anymore.
No,
beyond jealous right now.
Yeah, I am totally
Beyond
jealous. So
jealous.
I'm going to go back to your grade and take 20% off just to make me feel better.
I'll be here for the next
Okay.
2 classes. So
Okay.
yeah.
Well,
What if she brings you back a souvenir?
I don't think she's allowed to bribe me, but that would be a nice thought.
You mail them a postcard.
Not what I was thinking. She could bring me back a ticket to Hawaii.
Oh yeah.
There you go.
Yeah. They actually tickets right
2,
now.
my wife,
Right.
definitely.
Prices weren't too terribly bad. The round trip was $350. So nothing.
$350?
Yeah.
It's not too
God.
bad. Till you get there, and then you got to get a hotel and buy gifts.
No,
Well,
she
right.
has a friend.
And
I'm
spend
staying with
thousands
my
of
best
dollars
friend, yeah.
elsewhere.
Yeah.
So
That's
Okay.
cute, though.
Bye-bye, guys. I'm off to have a snooze.
I have a question real quick.
Yes, Isabel, question.
It's for the assignment you gave me an extension on. The
Uh-huh.
chapter 12. It was just one small part and one of the questions. Everything else I finished.
Okay, do you
Um,
want to share the screen or is it something you can say? I've given you permission, so you can share it.
Okay.
Right.
This is question 12. So I did everything else correct. It's just
Good. Oh, I've seen this question before.
the confidence interval. I don't know what I've done wrong. I have
Well-
salt pulled up over here to use.
No, you don't need to. I should tell you what's going on here. This is a special case. In this table, do you see how they've only told you the lower bound, which is very unusual? The
what?
0.10158. You see that guy there? 95% lower bound for P1 takeaway P2 is 0.10158. Do you see that? Yeah, there, right? If you go to your interval that you're having trouble with, the lower number is that 0.10158. So you could copy that and just paste it. That's half the answer now. Now you may have already done that, and then you changed it because you thought, well, that's what was wrong, but there's nothing wrong with that. Now, the other side of it, the upper limit. So if you scroll down a little bit, I'll show you what's going on here. They didn't tell you in that table up there what the upper limit was. So what we're going to do instead is we're going to make a big assumption.
Okay.
It's 1. Isn't that the biggest value a p could ever be?
Oh, okay.
Right, check it now.